Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Oh, good afternoon and welcome to Do the Math. I'm Michael.
And I'm Devin.
And in studio with us we have Braxton. And Braxton, if somebody wanted to get a hold of us, what would they need to do?
For math homework, call HELP in Bakersfield 636-4357. Toll free 1-866-636-6284. For the email, dothemath@kern.org. We are online, dothemathonline.net. And on social media, Facebook, Instagram, Twitter, and YouTube.
All right, beautifully done right there. Now, Braxton, why don't you let everybody know where you go to school and what grade you're in?
I go to Chipman Jr. High, and I'm in 8th grade.
How is 8th grade?
It's pretty fun.
Yeah?
It's hard to get used to the whole online aspect.
Yeah, trust me, I think it's a little hard for everybody to get used to the online aspect as far as students and instructors at the same time. So, this is your last year before high school. What are you most looking forward to in high school?
Just having a good time, getting good grades, obviously, and just having a good time.
Good. Well, you know what? We've got a moment or two. What I'd like to do is just do a quick little problem with you right now, all right? Because I know you're working on slope-intercept form. So why don't you head on over to the board, and you and Devin are just going to discuss for about 2 minutes what you know about slope-intercept form right now.
Okay. So, for this, you're going to just take a random point, and let's say it's 2, 4. So it's going to be rise over run. So, 2 over 4. And then it's going to be rise over 1. So 1, 2, and then all the way 1, 2, 3, 4. So you're going to.
Oh, if that's 2, 4, we may have to reconfigure where that point is, right? Because it looks like that's over at 1, 2.
We're just gonna.
Yeah.
Oh, whoops.
When in doubt, circle things.
So 2 over 4. So that's gonna be 1, 2, and then 1, 2, 3, 4. So it's going to be 2 over.
Now, when we lay out coordinates, we start off with the x-coordinate first and how far away from the origin it is, right?
Yep,
so,
I totally.
So instead of redoing the points, why don't we figure out what this point would be called, right?
It'd be 4, 2.
Yeah, let's go ahead and call that 4, 2. So if we have another point, let's say even the origin, where does slope-intercept form come into play?
It's when you have y equals mx plus b.
Now, when we hear slope-intercept form, there's 2 words there, right? Slope and there's intercept.
Yes.
So when we think about a slope, think it just without thinking about math. What do you think of when you hear the word slope?
Just like a little loop-de-loop.
A loop-de-loop. Have you ever gone skiing?
No.
Have you ever heard of people skiing or seen it?
Yes.
So when people go skiing, they don't go like on kind of like a flat surface,
No.
unless it's like cross country. It's on like a giant steep hill.
Yes.
So what those are called are slopes. And slopes are defined by basically how steep they are, right? They're either really high, really low, or maybe a little bit more gradual in how they incline, right?
Yes.
So when we talk about m being the slope, that's describing how steep the line is.
Yes.
Now we also have another term here, intercept. When you think of the word intercept, what do you think of?
Something crossing over it.
Yeah, like if it's football, an interception where a throw goes and somebody else catches it, right?
Yeah.
Or you target something and you get in the middle of it. So an intercept is where something crosses. So if we have this line, let's say it's going like this, right?
Yeah.
And what we're looking at when we talk about the intercept is where that line comes across. And whatever that value is on the y-axis, that's the value of b. So what slope-intercept form is really just describing is the line itself, how steep it is, and where it intercepts the y-axis.
Good.
Yeah.
So that way you guys got a little basic understanding right now about slope-intercept form, and that has to do with today's Math in the News. All right, in today's Math in the News, actually an article that was a strip out of the Wall Street Journal this last weekend. And I don't know, you guys may have heard about this, but there was a young lady about a month ago, and her post went viral because she wanted to know on TikTok whether math is real. You think math is real?
Yeah.
Okay, well, yeah, she had a question about, like, is math real? Okay, so mathematics is based on logic, not evidence. Take the equation y equals mx plus b. Funny, that's exactly what you're working on right now. Okay,
Challenge accepted.
and then the young lady mentions a perplexing example to deal with that. Now, in the article, I'll show you the little graphic they've got here. So there's y equals mx plus b. So is that kind of like when you first started this, how you thought about this?
Yeah.
Yeah, it's kind of like, all right, well, great. What am I doing with this right now? Okay. So the equation for a straight line didn't come about until a bit later on. The idea of manipulating unknown variables represented by letters has deep roots historically, but it wasn't developed into algebra until the 9th century. The linking of algebra and geometry had to wait even longer than that, until the concept of coordinate systems. René Descartes, a philosopher, came up with the Cartesian plane. They take Cartesian from René Descartes' name. That's why it's called a Cartesian plane, with the XY coordinate system. And that's what you're going to be working on in a little bit. So we can see that this article talking about the slope-intercept form is exactly what Braxton is working on today. And that is where the Cartesian plane comes from. And that is today's Math in the News. So we've got a quick moment, and I know you're going to get back to your point slope intercept form in a bit. But what I'd like you to do right now is a problem with exponents. And you're familiar with exponents, correct?
Yes.
All right, because today is a very special day. Today is September 16th. Do you have any idea why today is special?
No idea.
It's because you're on the show.
Huh.
That's the first thing. But it's also special for another reason, all right? Have you ever heard of the mathematician named Euler, spelled E-U-L-E-R?
Never heard of him.
Never have? It's a big day for you again today, right? So you're going to learn about Euler, all right? 16 is the only number that can be written in a reverse power way. Okay? So, head on over to the board, young man. What I would like you to do is I would like you to write 4 to the second power up on the board.
Like this, or like
There you
the
go, perfect.
value?
Ooh, look at that.
That's it.
Okay.
What does that equal?
It equals 16
How do you know that?
because exponents is it's 4 times itself
Right.
equals.
Now, Euler said that 16 is the only number that can be written in reverse powers. So if we have 4 to the second, how can we reverse that?
2 to the 4th power.
So write 2 to the 4th for me. Now figure that out. What is that?
That equals 16.
How do you know? Because it looks like
Because-
it could be 8.
So 2 times 2 equals 4 times 2 equals 8, and then times 2 equals 16.
There you go. So 16 is the only number that you can write in reverse powers.
That doesn't
there you go.
include like when you have the same value as its own exponent, like 1 to the first power.
Right. So there you go, nicely done. On the 16th day of September, the day that Braxton is in studio with us here on Do the Math. Hey, do remember we have phone tutors available until 5:30 most Tuesdays and Wednesdays throughout the school year. The phone numbers are at the bottom of your screen periodically throughout the program. Right now we have an opportunity to head out to Shafter and learn a little bit about wings and airplanes.
It is time for math in the real world, everyone's favorite part of the show. We are here today, man, what a neat place. We're here today at Woodwing Specialty, and we want to speak a little bit with the owner of Woodwing Specialty, Pete Plumb. Pete, we are glad that you could join us today. Thanks so much.
Welcome to my shop.
Yeah,
It's great
this
to be
is
here.
cool. Tell us where we are and what the heck happens here, because there's a lot of really cool looking stuff here.
Well, this is an FAA-approved repair station for wood aircraft structures. So I don't do any aluminum work or anything like that, no riveting or very little because I don't like it. But I do like to glue and nail little tiny pieces together to make these big, huge wings that hold up large airplanes. These are airplanes that weigh 3,000 pounds. And some of them carry one person, some two, some four.
What a
Yeah.
unique deal. So these are a little bit smaller airplanes than some of the ones we might see in the air, but they're made out of wood, and that's a
Right.
different type of deal. How did you get involved with this? Because this is a unique niche in the aviation area, right?
It is a unique niche. Back in the early, in the early 1900s, all the way up through World War II, all these airplanes were made out of wood. Aluminum aircraft structures didn't come in till after the war, pretty much. So these wings that I'm working on now date back to the 1940s mostly. And there are very few of us that maintain these because it's not taught in aviation schools anymore.
Right.
So
And they don't build them brand new anymore either, right? Is that
They
true?
don't build them brand new.
Okay.
And I'm one of maybe a handful of people that even know how to do this kind of work anymore. So it's very unique.
Very unique. And so because it's so unique, I really want to know, how did you get started in this? Because it is different. It's so neat.
Well, I was 18 years old. I was out of college, and I was really into hang gliding, and I got a job as a hang glider test pilot at Vern's Wing Shop here in Bakersfield. And when the hang glider part of the business folded, I was out of work, and I asked him if I could get a job there building wings, and this is the kind of work they did. They did mainly Stearman wings for crop dusters. And they put me to work on that, and I was there a year and a half, and then I ended up starting my own and went into business for myself.
And you've been here ever since.
I've been here since 1976.
Oh my goodness, man, that is super neat. So, just as a ballpark, how many customers do you have? Do you have regular customers? You have people who find you brand new, they don't know where else to go? Like, how does that work with the people that you work with?
I have repeat customers.
Okay.
And I do have new customers. So now that I've been in this 42 years and I'm pretty much at the top of my game, people know who to call, I mean,
bet.
for wood aircraft structures.
Yeah,
So,
yeah.
and I do the engineering. I've studied the math, and I know how these things work, and so that gives me an advantage over just somebody that's a mechanic.
Right. Right, that makes sense. Now, speaking of advantages, can you tell us maybe one advantage of a wood aircraft over an aluminum aircraft? Is there an advantage there that can be said, at least with all the technology that's out there?
Well, we have an example over here of an airplane that I built myself, and it's made completely out of wood, and the cost of that was extremely low. You can buy the Sitka spruce and the mahogany plywood that go into these airplanes for very inexpensive, where aluminum is a lot more expensive.
Sure, and you have to have specialized material, I'm sure, with aluminum, like you said, riveting and whatever else.
Right, and so I would say the cost is the biggest advantage to the wood. And then the other advantage is that anybody with just rudimentary wood tools and a little bit of woodworking experience can do this.
Yeah.
It's not really all that specialized. Now I've developed my own techniques for production, and I've been in production for a long time. So I've got a little bit of an advantage there.
Right. Certainly, no doubt. Well, we want to see a couple of the things that you are working on here in just a little bit, and of course, we want to know a little bit about the math that goes on, because something like this, there's got to be some math behind it all.
There is. It's algebra, and there's some trigonometry.
Okay.
There's geometry. That's about it. I mean, it's pretty simple stuff, really.
Good. So with some simple tools and some simple math, who knows, we could be making some wood airplanes by the weekend, right?
Absolutely.
So when we come back in our next segment, we want to see a little bit more specific about what's going on here. But right now, we'll head back and do some math in the studio.
All right, thanks for that, Scott. And excellent that these guys are doing that out there at Shafter Airport, and we'll look forward to some more of that later on this afternoon. We do have phone tutors available until 5:30, but more importantly, in studio, we have Braxton, an 8th grade student. And you ready to do a few problems now?
Yep.
We've discussed a little bit about this, but let's go ahead and write an equation for what you've got up there. So explain to us the points, what you've got, and what you're going to do.
Okay, so it's the point is 0, 2, and a negative 5, 0. So on that point, it's going to be, because this is where 0 is, this is the origin. So it's going to be 1, 2, 3, 4, 5. That's where the point is, 0, 5. And then this is the origin, so it's going to be 0 for the y, for the x-axis. So you're not going to move at all this way. So, but it's 2 for the y-axis, so you're going to move 2 this way. So going by the formula that we know, y equals mx plus b, we can tell that, so y and then equals 2x plus negative, oh no, it's not it. We're just gonna pretend that never happened. It's gonna be y equals 2x plus
rolling. We're live.
0. So you're going to do negative, because you want to just have x. So negative 2 is 0, so it's just x. So then it's going to be negative 2. So then that equals negative 2 because 0. So x equals negative 2.
So this isn't necessarily an equation we want to solve. What we really want to do is just identify it in slope-intercept form. And what you did really nicely was you identified, the points where it crosses the y-intercept. I want to start off with that. Remember what we talked about with slope, steepness, and then intercept, right? Where it intercepts the y-axis. Let me ask you a question. Where does this line with the 2 points that we've identified, where does that cross the y-axis?
It crosses on 2.
So that's going to be our b, right? That's going to be our intercept, positive 2, okay? So right now we have half of our work done for this equation. Y equals something x, we don't know what that m is yet, that slope, but we know what this is. We know that b is positive 2. So now we want to find out how steep this line is. Now, you mentioned earlier when we talked about slope-intercept, you mentioned something called rise over run. How would you describe rise and how would you describe run?
So rise is when something goes up.
Okay, so starting from the 2 points that we have, what you want to do is you want to look at the difference between not just your intercept and the axis, but really you're looking to compare these 2 lines. So starting at 1 point, how does the point change between these 2?
So you're going to go up 2.
Okay, so I want you to hold on to that, right? We're going up 2. Great.
Yes.
So rise, it's going up 2. Now my question to you is, by how much is it going over from this point to the next one?
It's going up 5, over
so
5.
rise over run,
Yes.
and that's going to tell us our steepness. So our steepness is, it goes up 2 and over 5 between any, and that's just kind of a ratio. That's a relationship between any 2 points on this line. So that 2/5 that we've created actually represents the slope of the line. So we're not necessarily trying to find out what x equals here, but what we're saying is that if we plug in any 2 values on any point on this line. Whatever the x is going to go fit here, and whatever the y is going to fit here. And when we calculate these out, these two sides will be equal. So that's what this equation is. 2/5 x plus 2 will equal y.
There you go. Nicely done. All right, now let's go the other way. All right. So now we're going to graph the equation.
Would you mind going ahead and erasing everything here?
Yes.
Great.
Just like it never happened.
Do a nerd.
All right, and get that other side done. There you go. Thank you, Braxton. And you can get rid of the line you've got there.
Yeah.
Okay.
You know what? Get rid of that, everything.
Okay.
There you
Clean
go.
slate.
All right, so here we go. So write down the equation. Okay, so we've got 3y
3y
equals 2x
equals 2x
minus 6.
minus 6.
So now what we want to do is, in order for us to be able to graph this, we need, at the very least, 2 points.
Yes.
In addition to that, we may want to simplify this so that we have a standard slope-intercept form. Remember last time you said that we wanted to get x by itself without a coefficient? In slope-intercept form, we actually want to have something attached to the x so that we can identify the slope. But what we want to identify is a way to get y by itself. So is there a way to simplify this linear equation so that we have the variable y without a coefficient?
Yes. So you're going to do plus, so that's positive, and bring that over here, right? So you're going to do plus 2 to get rid of this. And then you're going to do...
Well, remember, if it's attached to a variable, we can't simply subtract it away unless we bring it over to the other side. And we don't necessarily want to do that. Let me ask you this. With y, take a look at that 3y on the left side of the equation. What can we do to that to get it by itself? So literally, what's the relationship between 3y and y? What do you do to this to get to this?
You subtract the 3. Take
Well,
away
it
the
wouldn't
3.
necessarily be subtraction, right? Like if I have 3 of something, right? And I want to proportion out so I have 1 of something, would I have to like divide it so that it would be, so what we're really looking to do here is divide. So what do I divide 3y by to get to y by itself, or 1y?
3.
3. So that's what we're looking to do with both sides here. Whatever we do with one side, we're going to do with everything on the other side. So we're going to have to divide negative 2x by 3, and we're going to have to divide 6 by 3. Which one of those do you want to do first?
Now, it's not negative 2x, it's just 2x.
That's right, because it was originally laid out there.
Right.
So we
So
can
let's
divide
just
2x.
rewrite the equation again.
Here we go.
Okay.
Great start.
There you go. 3y
3y
equals 2x.
equals 2x minus 6.
That's going
There
to be
you go.
plus. Is that minus 6?
He's fine.
Minus 6.
Okay, great.
Right?
He's got it.
So we're going to divide everything on one side by 3 and everything on the other side by 3.
Okay.
Which of those terms would you like to divide by 3 first?
We'll do
2x or, well, the 3y. Sure, let's do that. We get y by itself.
it's just equals to 1y.
Great.
So then you're going to divide this. Do I solve this first?
You can, yeah, go
Okay.
ahead.
So this is going to be. You would have to have the x right here.
You don't necessarily need the x right there because 6 by itself is a constant. Let me ask you this. What is negative 6 divided by 3?
Negative 6 divided by 3 is negative 2.
Wonderful. So there is our constant there, what we consider our b, and that's going to be really important here. Now, when we think about 2x divided by 3, let's start off with just the 2 divided by 3. Is there a way that we can represent 2 divided by 3? Maybe differently than with a division symbol.
Like, whoops.
Well, even without long division, we could work it out and calculate, but, for the sake of precision, couldn't we also write 2 divided by 3 as 2 over 3?
Yeah.
So isn't that more precise than trying to come up with a repeating decimal forever?
Yes.
There's our slope right there. 2x over 3 is 2/3 x. Now here's why that's important. Remember, this is slope-intercept form, right? Let's go ahead and create a set of axes there intersecting, okay?
Okay.
Now, if you look at our slope-intercept form, y, and we could say y, we could say 1i, but it equals y. Y equals 2/3 x minus 2. Remember, whatever's attached to x represents the slope, and whatever is attached to the b term is our intercept, the point that exists where the line crosses the y-axis.
Yes.
So if that's negative 2, we know at least 1 point on that line.
Yes.
So go ahead and put the intercept at negative 2 on the y-axis.
Right.
So we
there.
know that we have 1 point at 0, negative 2. Now the key to creating this line is finding another point. But since you know the slope of this line, you could start at that and then find the next one by going rise over run.
Yes.
So by how much do you go up?
You go up by 2.
And then
so
you go across by how much?
3. So it'd be right there.
So what would that point be on the line?
It'd be 2/3. 2, 3.
It'd be across by how much? So
Across
from the
by
origin,
2. Or up by 2 and across by 3.
Okay, so what we identify this point as?
3, 2.
Well, if we start here at the origin, we go across 1,
Oh,
2,
0,
3.
3. 0,
It's
3.
3, 0. Right.
I was starting from right there.
Yeah, you always want to compare points when we
On the origin.
plot them compared to
Yes.
the origin. So we have 0, negative 2, and we have 3, 0. Could you do me a favor? Could you connect those 2 points with the line and then continue that all the way through? That is the line. Not only is it 2/3 x minus 2 equals y, but it's also 3y equals 2x minus 6.
There you go. Nicely done, guys. See that? We're making you work today, huh?
Yeah.
There you go. Well, you know what? That's exactly what we like to do, is help you out with these types of problems. And for some great work right now, you've got yourself a meal courtesy of our friends at Broken Yoke. So congratulations on that. Phone tutors are available until 5:30. We'll be back with more right after this.
We're back with math in the real world. And man, this is real world stuff. Look up in the sky. You see those airplanes flying, and Pete's going to tell us a little bit more about how they get up there. So everybody's interested about, I know I'm interested in how that happens. You got a little bit of information here for us, and there's all kinds of things to look at, but real generically, right? Real simply. This is the side section of a wing. How in the world do we get this big, huge aircraft, or smaller aircraft in your case, off the ground? I mean, it's got some weight to it.
Sure.
Right? You can't just throw it up there and it stays. Lift is kind of what we're looking at, right?
Lift,
Yeah.
and lift is generated by the wing, obviously.
Okay, so if we're looking at the wing from the side view,
Yeah,
what's
it looks,
happening here?
it looks
Where's the
like
force?
this. This is
Okay.
what we call an airfoil.
Okay.
And there's many different designs of airfoils. It depends a lot on how fast the airplane is, what its purpose is. And there's many different airfoils. And what we do as engineers is we choose the correct airfoil for the airplane. Now, I want to say this, that if you can take a flat plate that's angled to the wind, if the air is blowing this way, what happens is it can't go through there, so what happens is it deflects down, doesn't it?
Yeah.
Well, that creates a triangle, basically, because here it was coming straight in this way, and now it's deflected. And this is the amount of lift that will produce.
Okay.
Now, the problem is what happens when the air is attacking here is it starts to burble over the leading edge. This being the leading edge if the wing is going this way. The air will actually start to burble, and it'll also start to tumble over the backside as it goes off. And that is a loss of lift. So what the shape that we design does is it actually smooths the air out so that there are no burbles. And the better we get this to flow, this is called laminar flow, the better it flows over that airfoil, the longer it stays lifting. Okay? At some point, when the air is attacking, we call it the angle of attack. When this is called alpha. When alpha gets too high, then even an airfoil-shaped airfoil will start to burble, and that's what we call the stall. And it doesn't lose complete lift. It'll lose most of its lift, but it won't just fall like people think. It will. You get this wing out there, it's still going to be developing some lift.
Sure. And we have all kinds of forces going on with an
Right.
aircraft, right? You talked about lift,
Right.
but of course counteracting the lift is the weight
Right.
of the vessel,
Right.
right? And that's going to be, those things, I'm assuming lift has to be bigger than weight. In other words, it won't get off the ground, right?
Well,
The force of the lift has to be bigger than the force of the weight?
the lift is going to equal the weight
Okay.
as long as the airplane is in equilibrium.
Okay,
So
right.
And if it's accelerating, that means that the thrust is greater than the drag.
That makes sense.
If it's decelerating, then the drag is more than the thrust.
Gotcha. And if
Now-
anyone's looked out the window of an airplane and seen on a wing, they have the little levers that go up, and that's making more drag, and that's how it decelerates. Is that correct? I hope I'm right.
Somewhat, yes.
Okay, good. At least I'm a little bit right.
What they are is called spoilers. You'll
Okay.
look out on the wings, and there'll be a flat plate will come up this way, and
Right.
that's a spoiler. And the air coming over that wing, it gets tumbled like that,
Right.
and that will create a lot more drag, and the airplane will come down.
Okay,
Okay.
gotcha.
Now you'll also find that they will drop what we call flaps down here.
right.
Now what those flaps do is increase the lift, because here again we're going to deflect more air down.
Yeah, and that goes back to the example you had of the flat wing and the triangle. Yeah,
That's
that
right.
makes sense.
Yeah. So on the jets, they actually do what they call Venetian blind flaps, where they'll have flaps on flaps. So there'll be a flap here, and then it'll have another flap like this. I mean, they really get serious about directing that air downward.
Right. Well, they have a little weight to get off the ground, so that makes sense.
And that's why these things can go 500 miles an hour and yet land at 100 miles an hour. That's that weight it doesn't change. The weight doesn't change.
Right.
The air density doesn't change, but the thing that we can do is increase the lift of the wing, and that'll allow it to slow down. And I can show that in this formula.
And there's all kinds of formulas we can use here. With like a little bit of algebra, we have a lot of variables that can change.
Right.
And one of the things you just talked about was the air density. Is that right?
Air density
Okay.
changes.
So that depends on where you're flying. So,
Right.
So here in Bakersfield, can you give us an
Sure.
idea of what the air density is like compared to somewhere in the mountains or somewhere next to the ocean or something?
Sure, down at sea level here, the air density is a standard weight of about 14 pounds per square inch, okay? On our bodies right now, 14 psi we call it.
Okay.
Up high, you'll have maybe, it may go down to as low as 6.
Okay.
Yeah, and the way we do it in aerodynamics is this function Q here, and Q represents the half of the air density, which is specified as rho, and at sea level, rho equals 0.002378. That is slugs, and that's in slugs.
Oh man.
Which is, again, is an imperial unit
Right.
of acceleration of mass,
Yeah.
okay?
And this is such an amazing science, and usually science is done with a metric system, but we were talking earlier that aviation is done in imperial units, and we got to talk about that. Man, there's so much stuff to talk
Yeah.
about. Man, it's so cool. So when we come back, we'll talk a little bit about the units that are used in aviation, maybe check out some wings and the design that they are made in to create lift. Gosh, so much more to do here. Back to the studio for some more math problems.
All right, thanks for that, Scott. And also, you know what? We've done a lot of things with aviation in past years here on Do the Math. Nice to have Pete and learning a little bit about more aviation right there. We do have phone tutors available until 5:30 this afternoon. We've got Braxton, an 8th grade student, in studio with us. You all through with that point slope stuff?
Yeah.
Yeah, all right, let's move on to something else. Debt. All right, let's take a look at the problem right here. This is something that, you're not saying that you're going to be in debt, but you're going to have to worry about having money at some point in your life and then having an interest applied to that. All right, so let's take a look at the problem. You borrow $300 from a payday loan. All right, so maybe write $300 up there so you've got that information. And you're going to have to pay 20% interest every 2 weeks. There you go, put up that important information. So it's 20% every 2 weeks. So you just put 2 weeks, so every 2 weeks you're going to get another 20%. All right. Now the problem says, how long until your debt doubles if no payments are made? So you're not going to make any payments at all. Right now you borrowed $300, you owe $300, okay? But in 2 weeks, you're going to owe 20% more than $300, okay? We want to know how long will it take, how many weeks will it take until you owe at least twice as much. So it's got to be over $600 that you then owe. That's what I want you and Devin to figure out.
Okay.
All right, go to it.
So, if you owe, here, I'm just gonna make this smaller. So, if you owe $300 and you have to pay 20% every 2 weeks or 14 days, let's just make this decimal form. So, for the percentage, you're gonna move that over 2 times. So, it's gonna be 0.2, like 0.2 of this every 14 days or every 2 weeks. So you're going to do 0.2 every 14 days. So
So one thing I would advise is as you're getting ready to calculate that is maybe make a little table and put 2 weeks and then next to it how much you owe. There you go. I think Devin's getting it set up for you.
So we can do one column with weeks, and then we'll just put the dollar amount. So right now it's 0 weeks, right? After 0 weeks, we've borrowed the money, we owe $300. We got to pay that $300 back. But after 2 weeks, that amount's going to change.
yes.
So that's what we're trying to figure out, is by how much is that amount going to change by?
So you would do 300 times 0.2. So
Well, what's nice about multiplying by multiples of 100 is we got a couple of zeros to work with at first. So,
yes. So this is where the decimal point is. We're just gonna erase that.
all right.
So 300.
Well, think about this. What would 300 times 2 equal without the decimal point?
600.
Okay, go
So-
ahead and throw that in, but keep in mind that decimal value. So there we go. So 60. So what does that 60 represent?
That the increase.
The increase. So instead of it just being $300 after 2 weeks, how
It's
much
gonna
is it
be
now?
360.
360. Okay, now that's great. Let's go ahead and jump forward in time another 2 weeks. So how many weeks later is that going to be now?
4 weeks.
4. Okay, now we're not just adding the original 20%. Now we're paying 20% of $360. So that's where this can be very dicey if you're not aware of it, if you're not cautious of it. So we owe 360 and they're going to add 20% to that 360. So how would we figure out 20% of 360?
You would multiply that, so 360 times 2, or 0.2, but
Right.
we're going to put that decimal right behind the 0. So that's going to be 0, then 12.
Well, remember that
Oh,
there's
yeah.
a decimal point.
Yep.
Yeah. Okay.
So it's going to be 0, then 12. So that's going to be 672.
Okay, so what does that 72 represent?
That represents the increase.
So it's going to be $360 plus 72 more dollars.
Yes.
What would that mean that our new debt is?
It would be
We're at 6 tens and 7 tens. We're adding those two together. So 6 plus 7.
yes. I did it wrong. Circles matter.
Circles matter. So 6 plus 7, 13. Great.
13.
And
So
then
it's
bring
going to
that
be
one up.
$432.
So our new debt is $432. Absolutely. So after 4 weeks, we don't owe $300 anymore. We owe $432. So go ahead and throw that on the table now. As we jump further in time ahead, 2 more weeks. So how many weeks ahead are we now?
6.
And now we have another 20% on our new debt, $432.
So 432 plus or times 0.2. But we're just going to leave that as 2.
Now let me stop you right there. Before you, because we have a couple of steps here, right? We have to multiply by 2/10 and then add that to 360.
Yes.
When in reality, what we're looking for, we're not just looking for the original plus 20%. We're looking for 120%. that 100% being the original and 20%. So maybe instead of multiplying by 0.2, we multiply by 1.2. So that's going to allow us to do this calculation in one step instead of two.
Right, and I'm glad you brought that up, because when you guys got all through, I was going to mention that you could cut out a couple of steps here by multiplying by more than that 100, making it 120% every time. So that's good that you guys got that little shortcut kind of. So go ahead and keep doing it that way.
So
Okay,
we're going to multiply by 1.2 because that represents 120% of the original value.
I'm just going to multiply it like it's a 12.
Wonderful.
And then, so 1 and 2, and then the decimal point's right there. So
You can bring that decimal point in at the end after the fact, so we don't even need to worry about the yet, as long as we remember to bring it over. So we're going to do 432 times 12.
yes, just make that clearer. So 4, 6, and 8. Then we're going to put the 0 there. So it's going to be
Right.
2, or yeah, 2.
Yeah, you're right, because we're
3,
essentially multiplying 432 by 10. Man, great numbers to multiply by here.
So 4, no, we're going to start at the bottom because we're on the very left, right. And then 8, it's going to be 11, so 5,180.
Well, remember we have to bring a decimal place
yep,
over at the
yep.
end, right?
So we're going to owe 51.
Well, it's only one decimal place because
Yep.
it was 1.2.
Five.
So that brings us to $518. And, oh, that's a neat trick. And I don't think I can get out of that. Could you write the 0.4 at the end there?
Yep.
Okay. All
Now,
right.
do me a favor, because I've got a problem with this. You are not going to go to the store and go, I'm going to pay you $518.4, are you?
No, you're going to say, I'm going to pay you $518.40.
And how would you write 40 cents?
Like,
Thank you very much. That makes the old man a little happier now. Thank you for that. Continue on your way.
Look, the code would have gotten that. Let's go ahead and go to our two more weeks ahead, right?
Because
All
remember,
right.
you got to double the amount that you previously borrowed.
Now-
So you're almost there.
What do we need to get to double that amount? What are we looking to surpass?
600.
600. We feel like we're getting close. And if you notice, that increment is growing every time.
Yes.
So it's growing by more every 2 weeks that pass. All right. Go ahead and let's figure out our week 8 debt.
So 518.4
And
times 1.2. So we're just going to act like this is 5,184 plus.
so we're going to have 2 decimal places to have to come back to.
Yes.
at the
Right.
end.
Now,
Okay.
Devin, are you able to move that screen, or do you want me to? So
Why don't you go ahead? Yeah.
there we go. That way you've got a little more room to do your calculation.
Space is the
Yes.
place.
So 16, 3, and 10. And then 0, 4, 8, 1, 5. So 8, 12. Or no, that's 10 actually.
You got it. You got it.
10. And that's going to be 11.
You're still going to have that 1 up there that you carried over, right? Because 6 plus 4 is 10. So
Oh,
you bring
yep.
1 more over.
So that's going to be 12.
Great.
Then 6. So it's going
Hold
to
on there,
Well-
brother.
So we have 0 plus 1 in the thousandth place, right? In the thousandth
Yes.
place, and then you brought 1 over from the 12. So it's essentially 1 plus 1.
So, 2. Wait.
Well,
Yeah,
get
go
rid
ahead
of
and
the
erase that
6.
6.
Yeah. Because I think
Right.
when you lined up the numbers, you're kind of looking at them
Yeah.
Okay.
diagonally almost.
So we've got the thousandths place, 1 and 1, so that's 2.
Yep. Oh, in the thousandths place?
So you have 2. Yeah. So you have 200, and now you're gonna have 2,000 as well. Now you have the 10,000ths place, the 1 plus 5.
6.
6. So it looks like 62,208, but remember, you brought 2 decimal places over, and I think there's a decimal place right there for us convenient to work with right there.
Yep.
So what does that value represent?
$622.08.
Go ahead and throw that next to 8 weeks. Now, have we reached our target?
Yes.
Okay. So what this means is if we don't make any payments on this payday loan for originally $300, by the time we get to 8 weeks, or about 2 months, we don't owe $300 anymore. We owe over $600. And so we want to be careful, because if you're in a spot where you need to owe that much money in a short period of time, if you don't take care of it, it's going to end up owing a lot of money real quick.
There you go. Nicely done, guys. So it's going to take you about 8 weeks to do that. So next problem, go ahead and erase that board. Brand new problem for you. So you have gone to the store before, right?
Yeah.
And you've done some shopping, and you know that you need to look for the best price.
Yeah.
Okay, so we can take a look at the screen right now. We've got a couple of items. We're going to look at some origami paper. And you could buy origami paper. You could buy 120 of them for $3. Or you could get 200 for $4.99, 500 for $9.99, or 750 for $12.99. Which one do you think would be the best buy?
So we'll write that out in math form.
Is it 500 for $9.99, and then 750 sheets for $12.99.
So just looking at it right now, without doing any calculations, which one do you think would be the best buy? Meaning you're going to pay the least amount per sheet of paper.
I would say either the 200 sheet or the 750 sheet.
All right, well, go ahead. You know what? For the sake of time, I'm going to give this to you, and you can use the calculator, all right? So let's figure out the unit rate, okay? And if you want to do the first one, the 200 sheets, how do you think you're going to figure out what it costs for one piece?
You're going to divide the 200 by the money, the $4.99.
Okay, so you're going to go $4.99
$4.99
divided by 200.
Yes. That's going to be 2 cents.
Well, now what I want you to do is I want you to write everything down next to the 200. Write all the decimals that you've got there, everything you see on the calculator.
Okay, so 0.024495.
So obviously you're not going to go to the store and go, hey, I'll give you 0.02495 cents, right?
No.
What would you say?
I would say, I would round that and then say the price.
And what is the price now? If we're looking for just cents,
It would be 3 cents if you round it up. Oh, no, it would be 2 cents.
all right, now hold on. First you said it would be 3 cents, then you said it would be 2 cents. Which one is it?
It's 2 cents.
Are you sure?
I'm positive.
There you go. That's what I want. I want conviction. It's 2 cents. All right? All right, let's do another one. Because you thought the 750 one maybe?
Yeah,
So let's see if that's less expensive than 2 cents a piece.
so
So you got $12.99.
$12.99. Nope, I put 2. $12.99 divided by
750.
750 equals. It's 2 cents if you round it up.
Now hold on, not going to just you need to write down the decimal. We need to take a look at this.
So it's going to be 0.01732.
All right, and if you round that, what will it become?
0.2 cents, or 2 cents.
2 cents.
So then,
Does that mean that they're both the same unit rate, or that one has a lower unit rate than the other?
it has a lower unit rate than the other one.
So what tells you that one has a lower unit rate?
Because it's easy, there's a 2 is greater than 1.
Okay, so that's important to keep in mind. A rounded rate doesn't necessarily equal the actual unit rate.
Right, that's why I
Yes.
want you to keep the decimals up there.
That's right.
So do you need to try the other ones, or are we just going to stick with those two?
We can try the other ones.
That would be a good bet.
999.
Okay,
Whoops. 999 divided by 500 equals 0.01998.
well, that's an easy roundup. What does that round up to?
2 cents.
Okay, so that's a rounded unit rate, but is that unit rate greater than or less than the lowest unit rate we've found so far?
It's greater.
Okay, so it's not the lowest yet, right? It's not the
No,
best
it's not.
buy yet. So we
But
have one more
Dan,
to
I'm
check.
having you do this because I want you to realize that even though they're all coming out rounded to 2 cents, you can still go a
One's
little deeper
cheaper.
on that, right?
Yeah.
So go ahead and do the final one.
Okay, so $3.99 divided by 120. Oh, that's 12. $3.99 divided by 120 is 0.03325.
Now, after a couple of decimal values, you already know that that's not the best rate that you're going to find. In fact, it's probably the worst
Yes.
based on the value. What does that round to, just to be kind of clear?
3.
3 cents per sheet.
There you go. Nicely done. So overall, what would be the best buy?
The 750.
There you go. And why do you think they would make that the best deal? Why would a store want to get rid of 700 pieces of paper at one point?
Because you're spending more money.
You're spending more money, and they may want to get material out of the store, get more in, right? Plus, you'll see that if you buy certain things in quantities, it's less expensive sometimes than just buying a couple of things, right? And you might be, well, I don't need 750 pieces of origami paper, right? I would like to have only 120. But if you're thinking about the cost effectiveness of it, you may never have to buy it again for the rest of your life if you buy 750.
1,000 paper
All right.
grades.
Wonderful work right there. And we do have some more work for you, but we do have one last opportunity to head back out and check out what Scott and Pete are doing at Woodwing.
Math in the real world, talking about flight. We have a wing in front of us. We saw some math formulas a little while ago, but this is one you're working on, Pete. Tell us a little bit about what's happening, what's in front of us, and gosh, there's a lot that goes into this. A lot of internal structures that you don't see if the whole thing is complete, right?
That's right. This is a lower wing for a Stearman biplane.
Okay.
Now, they were used as trainers in World War II, and then in the 1950s and 60s, they made a great crop duster. In the 70s, they were replaced by modern crop dusters.
Right.
So a lot of these Stearmans that were crop dusters are being turned back into World War II vintage airplanes and by the owners. They were all made out of wood, and what happened to this particular one is for whatever reason, the pilot lost control on landing, and he dragged this rear spar on the ground, and the load was transferred to the support, and that's where it broke.
Okay.
And that's where these things will break, and that's what we call this is the highest moment. When we get into moments and moments of inertia, we're gonna talk about all that. But it broke right here. I was able to cut the broken part off right about here and splice in with a scarf joint to the old wood. And this is a FAA approved repair for this particular damage. In order to do that, I had to replace all of these with brand new pieces and splice them in. These haven't been done yet. I'm still working on this one. They've been spliced on the bottom, but not the top. And this wing will get completely repaired, and then it'll be covered with a Dacron fabric and a special aircraft paint called airplane dope. And it'll be, and this is a good example right here of fabric that's been doped, and it's very, very strong. So that's exactly what's going to happen here.
Wow. So it's a mix, looks to me, of some of the old wood that you could salvage and some new wood that needed to be repaired.
Right.
And ultimately, this has a very specific angle and a specific curvature to give this vessel the correct amount of lift, right?
Right. This particular airfoil is an NACA 2213.
Okay.
And NACA did a lot of research back in the 20s and 30s on different airfoil shapes that we were just talking about.
Right.
And this particular one, I happen to like this airfoil. This airfoil creates a lot of lift, it's low drag, but it worked perfect for the Stearman.
Okay. And can this plane go really fast? Or is this not so much for speed?
Not so much for speed. Yeah, it's for lumbering around and teaching students how to fly.
Right. Now, speaking about students then, that's a really good, you kind of jogged my mind there. This kind of shop is not on every street corner. I mean, it just isn't around. You have kind of a niche market here, but if someone was really interested in flight, right, and maybe even repairing some wings, where would they start? Where would you suggest a student started if they were interested in aviation?
I would say make sure you get your math background,
Okay.
algebra, geometry, get some trigonometry, and take your physics classes. The physics is really what makes this all make sense to you.
Okay.
So do really well in math, do really well in physics, and then you go to an aviation college, like there are several around.
Right.
And then they can teach you specifics. Now, there aren't a whole lot of us doing this aircraft woodwork anymore, so it's very, very much a niche, but there's still a demand. There's still 100,000 airplanes still on the registry that are made out of wood.
Wow.
100,000 of them,
Oh my
and there's
gosh.
only a few of us that repair them.
Yeah. So you really do have a kind of a niche market there.
Yeah.
Now, all kinds of things, all kinds of directions we could go with this conversation. We're going to have to come back and see you. But you obviously have a very specific structure you use. We could probably talk about engines and about how they make the force that goes into it,
Yeah.
about how much fuel something holds, and about the structure of the body of the. There's just all kinds of stuff to
Yeah.
do there.
There's a lot of trigonometry in here, and you can see the trigonometry going on in the truss here.
Right.
There's trusses, there's beams, there's, here's another truss, and there's compression loads, there's torsional loads, and I want to get into all that at a later time.
Yeah, no doubt. Gosh, there's so many exciting things, and ultimately, what it does is it gets something in the air, right? And
gets
that's
it in
probably
the air,
what
and
caught your
safely,
interest.
and
Safely,
safely.
that's right, and safely back down to the ground. That's
Yeah,
right.
so-
Well, we want to leave you with, of course, the famous Do the Math tile. We even picked a spot for it, maybe right here on the wing. I don't know, maybe not. That'll be inside the plane at some point, but. Thanks so much for your time. Gosh, we learned a lot, and I know at least I am, still intrigued about, maybe the other half of the shop or all the other things we could do. So we'll make sure we come back and visit you sometime
welcome
soon.
back anytime.
Gosh, this is a super cool place. Math in the real world does not stop, and we will be back next time. But right now, I know we got to go back to the studio and just a couple more math problems.
All right, thanks for that, Scott and Pete. We do have phone tutors available until 5:30 this afternoon. The phone numbers are at the bottom of your screen. And Braxton, we would like to say thank you for coming in this afternoon. Did you have a good time?
Yes.
That is the bottom line. What do you think is the one thing that you remember doing today that is going to be most useful?
Finding the best value for the origami paper.
There you go, right? Because that is something that you're going to be able to use all of the time. Just being able to figure out unit rate and doing that kind of thing is going to be valuable for you. And for coming in, we'd like to present you with an ambassador t-shirt. You are now going to be an ambassador. You know what that means?
No?
You're going to tell everybody about Do the Math. That's all you have to do.
Okay.
All right? So when you wear it around, people are going to go, hey, what's going on with that? And you tell them, hey, I got it up here. I know about unit rate, point slope, all that stuff, right? So you can do that for us?
Yep.
All right, excellent. Thank you for coming in today, Braxton. Once again, phone tutors are here until 5:30 this afternoon. And until we meet again, continue to do the math.
Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.